All right, people, we are going to do our second pH and pOH calculations. These are definitely the more complex functions that you will be asked to do. So you will need your calculator. So before we begin, please pause, go get your calculator, come back, because it's really crucial that you use that information in these presentations so that you can put these in your calculator correctly and figure out all the stuff about pH and pOH. Okay, so first things first, understand the log function for pH values. Okay, all of your pH values and all of your solutions are measuring that concentration of your hydronium ion. And that is going to range somewhere from 1 times 10 to the negative first molar to all the way to 1 times 10 to the negative 14th in molarity. Okay, and one thing that you might have noticed from those simple calculations is that the pH value will be the same as the exponent, but it'll have that positive value because the equation is pH is equal to the negative log of the concentration of the hydronium ion. Okay, this will be easy for everything that is obviously to the power of base 10, and your pH values will be a whole number if it is 1 times 10 to the whatever value. Okay, so if it's 1 times 10 to the negative third, your pH will be 3 and it will be an acid. If it's 1 times 10 to the negative 10th, it's going to be a pH of 10 and it's going to be a base. Very easy for if it's 1 to something because it's just basically figuring out your exponent. So what we're going to be doing in these next couple of slides is figuring out when it's not going to be a nice easy value. Okay, so here are 3 different sample calculations for the more complex ways of determining your pH values. So for each one of these, what we are going to do is we are going to figure out the pH of the substance and make sure that it makes sense. So is it going to make sense that it is an acid or is it going to be a base? All right, so looking at these 3 examples, you should be able to figure out which ones are acids and which ones are bases. So this first one, 0.001 molar HBr. HBr has hydrogen, it's hydrobromic acid, so this one should be an acid, and the pH value should be less than 7. Okay, 0.035 molar HNO3. HNO3 is nitric acid, so this should also be an acid and have a pH value less than 7. 0.035 molar KOH, there's an H here, but it's not an acidic H. You have to notice that it is a hydroxide. This is a base, so the pH value is going to be greater than 7. Okay, so let's take a look at this first one on the next slide. All right, so if we have a 0.001 molar HBr solution, okay, HBr is one of those 6 strong acids I told you to memorize, okay? So if we know that HBr is a strong acid, we know that it is going to completely break up into H plus and Br minus, and the H plus is going to come in contact with water and obviously make your H3O plus your hydronium ion concentration. So the hydronium ion concentration will be the same as the concentration of your HBr. So this is the value that you put in right here. Okay, so when we figure out our pH, pH is the negative log of the hydronium ion concentration. It's pH negative log 0.0010, which, if you haven't already noticed, is the same as 1 times 10 to the negative third. So when I go and I plug that into my calculator, I see that it is a value of 3. And that means that the pH of this is going to be 3. Does that make sense? Yes, it is an acid. It should be less than 7. Okay, so that one is pretty easy on the complex version. Okay, next we have 0.035 molar nitric acid. Okay, and nitric acid is another one of those very strong acids I asked you to memorize. So that means that you need to look at the concentration of this as well. for your concentration of your hydronium ion. Okay, the hydronium ion will be the concentration of your actual acid. So with that said, this is the negative log of 3.5 times 10 to the negative second. We can't just say that this is a pH of 2, okay? This is going to be close to 2, but it is not a 1 times 10 to the negative second value that we are plugging in. So when you are plugging this in your calculator, you have to plug in the 3.5 times 10 to the negative second. Do you remember how to do that? That would be the negative log in our calculators, the negative log of 3.5 e negative 2. And you have to use this E button, not this E button. We're going to get to that shortly. Okay, this is going to give you a value of 1.46, which means it is an acid. All right, so if you're still with me, now look at option C, 0.035 molar KOH. KOH is a strong base, so the concentration of the KOH will be the concentration of the hydroxides, not hydronium ions. So we need to be extra careful with this. In order to calculate the pH, we need the hydronium ion concentration. So remember that KW expression we went over? Yeah, we rearrange that. We have to get H3O plus by itself. That means divide both sides by KOH, and you get this value. All right, expression. H3O plus is equal to the Kw divided by the concentration of the hydroxide. You plug in that constant, 1 times 10 to the negative 14th molar squared. It's going to remove the squared and just give you a molarity of this. Now, this value, that 2.9 times 10 to the negative 13th molar, that is going to what you use for your pH. Okay, so then you do the negative log of 2.9 e negative 13, and then you get your value for that. Okay, now one of the awesome yet horrible parts about pH is that there's more than one way to solve it. So yes, you can do that 2.9 times 10 to the negative third and get a pH of 12.54, and yes, it is a base, and yes, that all checks out. Or from the original problem, when you knew that your concentration of your KOH is equal to the concentration of your hydroxide, figure out what the pOH is first. Figure out what the pOH is, okay, by taking the negative log of that value, getting a pOH of 1.46, and then determining what the pH is. pH plus pOH always equal 14. So 14 minus 1.46, ta-da, arrives you at the exact same answer. Which one is easier? I think this one's a little bit easier just because it's less of the E button, but I would still know both because sometimes it's going to be faster to do it the first way than it is the second way. Okay, so with that being said, we need to be able to be comfortable going back and forth between your concentrations and your pH. If the pH is equal to the negative log of your hydronium ion concentrations, you can get your hydronium ion concentrations from your pH. And that's where we go over this part, the inverse log of the negative pH. Okay, so what we do is we rearrange this to get an equation where the concentration of our hydronium ion or our hydroxide ion would be this does not mean 10 to the, okay, this is going to mean the inverse log. Okay, it is also referred to as the anti-log. And this is that special button on the calculator that you have all been tempted to use when doing your scientific notation. Okay, so on your calculators, okay, you are using these buttons. You have to type in second and 10 to the, and then you will see that is the inverse log function. Okay, that is different than the second and the EE button that you have been using right here for scientific notation, like 1 times 10 to the something. Okay, this is the 1/8. So this is what we have been doing all of that preparation since the beginning of the year for, making sure that you understand the correct buttons on your calculator. Okay, so if Olivia measures the pH of a soil sample solution and it has a pH of 6.2, what is the concentration of the hydronium ions? Okay, so the concentration of H3O plus is equal to the antilog of the negative pH. So what you do is you just simply plug in 10 to the negative 6.20. And when you are using your calculator, be very careful. Okay, your calculator, you should be hitting the second button, and then you should see that 10 to the x pop up, and you type in 10 to the negative, make sure you put negative 6.20, and then hit enter. Never leave a decimal, okay, as your exponent. That is so bad. You do not want to do that. All right, so when you do that, you will see that you end up having a concentration of 6.3 times 10 to the negative 7 molar. And that should make sense because that's going to be our indication that that was an acid. Okay, so that is a nice way for you to figure out the concentration of your hydronium ions from your pH. You can do the same thing for concentration of hydroxides and your pOH. It is the exact same application to the whole thing. You take the opposite of the negative on each side, you take the inverse log, and you get the 10 to the negative pOH concentration. So you can solve and figure out any of them from here. Now, this is the go-to slide for the entire chapter. So, star circle highlight, take a screenshot, a picture, whatever. But these equations will help you go backwards, forwards, in and out because there are multiple ways to solve these. Okay, the two important equations are your pH and your pOH calculations, and you know that they both add up to 14. So you can go back and forth between them. You will need to know some way, shape, or form that Kw expression, okay, where they have the concentration of your H3O, your hydroxide, and your hydronium ions together, and then you can isolate one or the other, and you can plug in the Kw value into any of those two spots. Okay, so this Kw expression is a constant and can help you get from concentration of one thing to another. And then obviously we can go backwards and forwards when it comes to our concentrations and our pHs. So you see that these guys are the opposite of those guys going with the antilog. All right, so make sure that you practice all of these equations. Yes, there is more than one way to solve them. So if you have questions, please let me know. But this is the go-to slide for the chapter. And that is how you calculate pH, pOH, concentration of hydronium ion, and concentration of hydroxide ion. So happy calculating, everyone.